This is slide number 61 and I am your presenter Asloob Mudassar. Coherent imaging transfer function with aberration. Up to slide number 60 we have discussed this topic, that is the coherent imaging transfer function but without aberrations. Now we are including the aberrations and we shall present that when the aberrations are incorporated, how would that look like, that is what how the mathematics is modified and what are the physical significance of including the aberrations. Coherent imaging transfer function of a diffraction limited aberration free system, which we may record as an ideal system, was presented earlier. For a real system, aberrations cannot be completely eliminated. How would the coherent or amplitude transfer function look like in the presence of aberration? So here we shall evaluate two things, that is the point spread function and the transfer function, and we shall see how these two things will look like when the aberrations are included. In diffraction limited systems, the spherically converging wave fronts leaving the exit pupil focus very well at the image plane. If the wave fronts leaving the exit pupil departs from the perfect spherical wave fronts, the wave fronts may not be focusing accurately at the image plane, resulting in image defects called aberrations. The focused image point will be blurred and will depart from perfect image point. One reason for the distorted wave fronts, especially in the region outside paraxial region, may be associated with the spherical shapes of surfaces in spherical lenses. So you see, if we consider only the paraxial region in the spherical surfaces, we can get rid of the, we don't need to incorporate the spherical, we don't need to incorporate the aberrations. But if we are including the spherical shapes and violating the paraxial regions, then of course the spherical aberrations must be included. Now if a system is designed close to aberration-free system, a few dust particles on the surfaces may be responsible for aberrations. So you see that if some particles, if our system is perfect, that is free of aberration, and if some particles, dust particles for example, are sitting on our optical systems, what will happen when the light will pass through, those point sources will act as scatterers, and you know that they may scatter spherical waves or they may act as point sources. So you see that they will make our system dirty, and the aberrations has to be incorporated, which is difficult to do mathematics such as scatterers. So it is better to have clean optics when we are using optical systems. Earlier we have considered pupil functions with 100% transmission within the aperture region and zero transmission outside the aperture. In order to incorporate aberrations, we shall model the pupil function differently. The new pupil including aberration effect may be labeled as a generalized pupil function, denoted as P bar as a function of xy defined below. So P bar as a function of xy is equal to P as a function of xy multiplied by e to the power iota k, and capital W as a function of xy. Here P without bar, that is the P on the right hand side, is the pupil function without aberration. And you know that we have multiplied some phase factor that will change the phase disturbance at the pupil function, and we have labeled it as given on the left hand side, that is the P bar in equation number 90. K is the wave number and W, capital W as a function of xy, is the path length error at a point xy of the pupil function P of xy. Path length error is the difference between two paths, one which contributes to ideal image point and the other which contributes to blurred image point. W of xy may take positive or negative value. K multiplied by W of xy gives the corresponding phase error. P of xy is unity within the aperture region and 0 outside the aperture region. A generalized pupil function may be realized by placing a phase screen at the exit pupil. So you see that if we have even a very clear aperture, we can use a phase screen at the pupil function, so that we can simulate this thing, that is if aberrations are present, how we can simulate them. So for the simulation purposes, we can place a phase screen over there, and we can also do the same thing for practical reasons. Figure on the next slide explains how outgoing wavefronts are distorted by the generalized exit pupil when plane wavefronts are incident on it. So you see that, look at the figure. The plane waves are incident from the left, and you know that at the object we have placed the phase screen at the exit pupil. We are not here we are not considering the shape of the exit pupil, that is whether it is circular or a square or a rectangle, but here we just want to demonstrate, and we have placed a phase screen at the exit pupil. And you know that when the plane waves will pass through the phase, will pass through the exit pupil, the distorted wavefronts will appear, as you can see on the right hand side of the phase screen. So you see that the phase these are actually the phase modulated form of the input wavefronts. And the caption is distortion of wavefronts by the phase screen at the exit pupil. So let's read the statements. Plane wavefronts are incident on a phase screen placed at the exit pupil. The outgoing waves to the right are phase modulated by the screen, which we may call as distorted wavefronts. The distorted wavefronts carry phase information induced by the phase screen. For an ideal imaging system, perfect diverging wavefronts incident on the entrance pupil will lead to perfect converging wavefronts leaving the exit pupil. So you see that we have given here the definition in terms of the illumination at the pupil plane and the illumination leaving the pupil plane. That is, if a perfect diverging spherical wave is incident on the pupil on the entrance pupil, that will lead to perfect converging wavefronts leaving the exit pupil. Figure shows both types of wavefronts from the exit pupil, forming ideal and blurred image. So you see that the leftmost is actually, you can see that this is our exit pupil and the wavefront is just coming out of the wavefront. You can see that a continuous wavefronts, these are actually the perfect spherically converging wavefronts. And you know that I have also plotted the dotted wavefronts, or you can say that these are the distorted wavefronts with dotted display. So these are the distorted converging wavefronts, and we have shown that both of these wavefronts, that is the perfect spherical converging wavefronts and the distorted converging wavefronts, are focusing at a point. So the sharp image is corresponding to the ideal image point, and the blur image due to these distorted converging wavefronts are forming a blur image point. And the caption of this figure is focusing of perfect spherically converging wavefront and distorted wavefront to ideal and blur image points respectively. So let's read some statements relevant to this. Figure shows both types of wavefronts from the exit pupil, forming ideal and blur image points. W of xy will be 0 when the distorted wavefronts overlap spherically converging wavefronts. Notice the central region of the wavefronts in the figure where the two wavefronts overlap. So you see that if the distorted wavefronts is exactly overlapping the perfect spherical converging waveforms, then you know that this capital W will be equal to 0, and the blur image and the ideal image will be the same in both cases because there is no distorted wavefronts now. W of xy may be regarded as positive, where the parts of the distorted wavefronts have lagged behind the reference spherical wavefronts, and negative where the parts of the distorted wavefronts have advanced the reference spherical wavefronts. So W of xy is the path length error seen by a ray as it passes from the reference spherical surface to the distorted spherical wave. For a coherent system with aberration, amplitude PSF, that is the amplitude point spread function, is obtained by replacing the pupil function P of xy in equation number 29 by the generalized pupil function P bar of xy, and the result is given below. So you see that we know that kappa is our amplitude point spread function. Here we have reproduced kappa using equation number 29, but here we have replaced P in that equation by the P bar, as you can see in equation number 91. So kappa of uv is equal to A over lambda zi double integral, and you know that we have here P bar rather than P because we are now wanted to include the aberrations into our system. And P bar of xy multiplied by e to the power minus iota pi over lambda zi, and within the curly bracket we have u into x plus v into y, and the integration is with respect to dx and dy as given in equation number 91. The amplitude transfer function is obtained by taking the Fourier transform of the amplitude impulse response and is given by. So you see that, as we know that the transfer function is obtained by taking the Fourier transform of the point spread function, which we have done in equation number 92a, that is we have taken the Fourier transform, and the Fourier operator has been sent inside the integral because the Fourier operator will operate only on the relevant coordinates, that is u and v. So you see that here we have given the Fourier transform of that one in the second step, forming equation 92b actually. So this is not 91b but actually 92b. So this is a capital Kc as a function of xy, and this capital C stands for the coherent. So it is the coherent transfer function, or you can see that it is the amplitude transfer function on the left hand side Kc, and you know that it is equal to A over lambda zi double integral P bar as a function of xy, and you know that when the Fourier operator has operated inside this exponential in the equation 92a, we have obtained delta of fx plus x over lambda zi, comma fy plus y over lambda zi. So you see that this is the Fourier transform we have evaluated, and now we have to use the property of the delta function in order to further simplify the integral in equation number 92b. And you know that we have written the integral in equation 92c as a delta of lambda zi fx plus x, comma lambda zi fy plus y, because we have taken lambda zi common from both parts of the delta, and you know that that becomes lambda zi square outside this integral, which we have represented as, you can see outside the integral that we have used the term lambda zi whole square. Okay, now we can use the, so you can see that 92c is explained. Now the 92d is written when we have used the property, that is we have replaced x in the pupil function, that is P bar of x. This x in the P bar has been replaced by minus lambda zi fx, and y in the P bar has been replaced by by minus lambda zi fy, because at these values of x and y the delta function will exist and the integral will vanish out, giving these values to the inside the pupil function, which is P bar. And you know that we have written 92e, where we have discarded all the constant terms outside, that is A lambda zi has been ignored and has been discarded, because the constant has no physical meaning when we are writing the transfer function. And you know that this is the coherent transfer function or the amplitude transfer function given in equation number 92e. And you know that here we have a P bar rather than P. Okay, now we have to use the value of a P bar, that is we have to use these arguments in the value of a P bar. Where is P bar? So let me show. This is P bar in equation number 90. So the variables of the P bar will be replaced, that is x and y will be replaced by its arguments which we have achieved after these processing. So you see that we have now the arguments of these P bar as lambda z I f x and lambda z I f y, which we shall plug in the equation that I have just shown. And you know that in this equation, okay, in writing equation 92e, we have omitted the scaling factor and the negative sign. So you see that here we have omitted the scaling factor and also the negative sign, because the pupil function is even function, because it is symmetric with respect to the origin of the pupil function, because the pupil function is centered at the origin. That's why we can omit the negative sign also. In writing equation 92e, we have omitted the scaling factor and the negative sign. Using equation number 90 into equation number 92e, the coherent transfer function for an aberrated system thus takes the following form. So you see that here this is in equation number 93. We have written the coherent transfer function on the left hand side, and on the right hand side we have written its form. You know that now we have not written P bar, but we have written in terms of P the original pupil function without aberration. But you know that on the right hand side of this pupil function we have some phase factors e to the power iota k w as a function of lambda z I f x comma lambda z I f y. So this is equation number 93. Now in order to obtain equation number 93, we have assumed some assumptions. We have made some assumptions which are given. So let's make the conclusions. The following conclusions may be drawn. Number 1, aberrations in a coherent imaging system did not change the bandwidth of the amplitude transfer function. That is, the cutoff frequencies remained the same as the aberration, as for aberration free system. So you see that in the 93, comparing with its counterpart, which was free of aberrations, you would see that the inclusion of aberration has not changed the cutoff frequencies of the transfer function. That is, the bandwidth remained the same. And in step number 2, aberrations introduced phase distortions. As you can see that on the right hand side we have the phase factor in equation number 93. The aberrations introduced phase distortions within the pass band. Phase distortions are never in favor of image quality. The fidelity, that is the resemblance of image to object, is severely affected by the phase distortions if magnitude of a phase error is a significant part of a radian. So you see that if this phase distortions that we have shown in equation number 93 are of significant values, that is even a small part of a radian, then you know that even this small fraction will affect the fidelity of the system. OTF with aberrations. Now we are going to discuss OTF with aberrations. OTF, what is OTF? You know that optical transfer function. And before that we have been discussing OTF in the form of normalized incoherent transfer function. So OTF is the normalized incoherent imaging transfer function, the incoherent intensity point spread function of an aberrated system can be obtained from the corresponding amplitude point spread function given in equation number 95 by the following relationship. You know that the intensity point spread function of an aberrated system can be given by the absolute square of the kappa. And you know that this absolute square of kappa is actually the intensity point spread function. And you know that this is what we have shown in equation number 94 by including P bar as a function of xy. So it means that P bar, whenever P bar occurs in an equation, it means that we are considering the aberrations in that system also, as shown in equation number 94, that we have included P bar within the integral. And so actually this is the same value of kappa as we have used earlier. But you know that this is kappa with the P bar, not with P. The OTF of an aberration free system was given in equation number 74. In order to transform equation 74 for the OTF of an aberrated system, we need to replace p of xy by the generalized people function, which is p bar of xy. The result is given below as in equation number 95. So k in, that is the incoherent. In as a subscript stands for incoherent. K stands, you know that, for the transfer function. So this is the incoherent transfer function, and you know that we have also used ABR in the subscript, which stands aberration. So this is the incoherent including aberration transfer function. So this is the aberrated transfer function of the incoherent system as a function of xy. And you know that we have written this equation. We have also written this equation without aberration when we used p instead of a p bar. Now we are using p bar. It means that we are including the aberrations, and the p bar has been used in the numerator as well as in the denominator. Now you see that to express p bar in terms of a p, we make use of equation number 90 as we have shown earlier. So we now want to represent p bar in terms of a p, as you see that you can see in equation number 96. So p is separated by its part which is exponential, and you know that we have used the same parameters, that is the arguments of a p bar has been replaced in the equation number 90, and we have shown this equation. Now you know that the numerator and the denominator both contains p rather than p bar, and you can also notice the exponentials on the with each p, because it is a part of the expression in equation number 90. And you see that you can see the exponential factors both in the numerator as well as in the denominator in equation number 96. Now our purpose is to simplify the equation number 96 so we can get some useful results. For that one, what we are going to do is that we are going to take the absolute value of both sides of equation number 96, and here we have shown the absolute value in equation number 97. And now we have to simplify this one. So you see that we have separated in equation number 98a, we have separated the exponential parts, and we have separated the that is the pupil function parts. And now we are going to apply this Schwarz inequality. And you know that in the Schwarz inequality you also are familiar, and we have also discussed in one of the previous lectures. And you know that the absolute square of k in with aberration as a function of xy is less than equal to when we separate out the two modulus on the right hand side. That is, one modulus is around the integral on p on the pupil functions, and the other integral is on the exponential factors. So you see that we have separated the two factors there. That's why our left hand side is smaller than the right hand side, and the same is what we have done on in the denominator. But you know that in the numerator, since our pupil functions we are discussing two pupil functions in the numerator and one pupil function in the denominator, it means that the weight of our numerator is higher than the weight of our denominator. That's why the right hand side, the whole value of the right hand side including the numerator and the denominator together is greater than the left hand side, which has absolute square of the k in, as given in equation number 98b. Okay, now we are going to do some simplifications over here. So you see that what simplifications we have made. Let's notice that have we made some simplifications over here. So I think that this is the same equation that we have written before, or perhaps we have separated, you know, that denominator we have also separated the two factors in the denominator, and you know that here we have actually combined the positive values over here. For example, in this, you know that we have combined the positive values of the numerator, and here you can see the exponential parts that we have combined the positive values in both, that is x plus this one. Okay, so let's move on to the equation number below the 98c, where we have done the simplifications. So notice this integral, the double integral, which is including exponential parts, and actually we are solving the part of the numerator here. You can see that we have incorporated the two exponential parts, and we are going to solve the absolute square of that integral containing the exponential parts. And you know that here what we have done in 98D, that we have e to the power we have applied this modulus now within the integral, because the absolute square of the integral is the same as the absolute value within the integral, and so we have taken the absolute values of the integrand in equation number 98D. And you know that the absolute value of the integrand, you see that when we take the absolute value of the complex value, you get 1 only, so we have obtained 1 only here. So you will see that in the numerator we have obtained 1, and the same in the denominator. So this is now the integral we have shown in 98E, in equation number 98E, the integrals corresponding to the absolute square of the integral in the denominator. And you know that again we can move the absolute square value within the integral, and again you know that it is unity, as we have shown in the last step of equation number 98E. So you see that from the numerator in the equation 98D, in the last step we have the double integral on 1 and operate with respect to dx and dy, and again you know that in the denominator we have solved the integrals of the exponential, and again we are getting the same integral. So both integrals given in the last step of equation number 98D and equation number 98E, both are equal and will cancel out, because one belongs to numerator, the other belongs to denominator. So the oversimplified result is free of the exponential terms, exponents which were present in the integrals over here. So we have got rid of these exponential terms in the integrals in equation 98C, and now we have obtained equation number 98F. So you see that it is a rather simple equation. So let's see what we want to do next is that we have so now what is the difference between equation number 98F and 98G? So let's see, we have, you know that the left hand side is the same, which is the absolute square of k in with aberration is less than or equal to the whole integral that we have given. You know that the difference is that the absolute square in equation number 90F is the absolute square of the numerator separately and the absolute square of the denominator separately. And in equation number 98G, we have taken the absolute value of the whole term on the right hand side. And you know that by this we can compare the left hand side with the right hand side, omitting the absolute square sign. So with the terms within the absolute square sign on the left hand side and on the right hand side will follow the inequality as given in equation number 98H. So we have the absolute square of the k in, because you know that the absolute square within the right hand side is actually k in without aberration. So this is the optical on the right hand side. We have the within the absolute square term we have the k in, which is the incoherent transfer function. So you see that we can now write the right hand side, the terms on the right hand side can be replaced by k in, that is the absolute square of the k in as a function of fx, fy as given in equation number 98H. So you see that we can omit the absolute square and the square values on both sides of equation 98H, and we can simply write that the absolute value of the incoherent transfer function with aberration is less than equal to the absolute value of the incoherent transfer function without aberration as given in equation number 99. And you know that we cannot omit the absolute value, because the left hand side of quantity may be negative due to the aberrations. That's why we need to keep the absolute value on both sides. If we omit the absolute sign on the right hand side with the incoherent transfer function without aberration, that would not matter. But you know that on the left hand side we have to use it with caution, because the k in with the aberration could be negative also at some points of fx value and fy value. So we need to use this equation. So remember that equation number 99 giving us very simple results, that the absolute value of the incoherent transfer function with aberration, that is the OTF with aberration, is less than or equal to the OTF optical transfer function without aberration. The modulation transfer function, which we call MTF, of an incoherent system with aberration is normally lower than the MTF of the same incoherent system without aberration. Both have the same cutoff frequencies. So these MTFs have the same cutoff frequency. Practically, it has been found that at higher frequencies, the MTF with the aberrations attains much lower values, and consequently, the MTF curve cuts the frequency axis at much lower values, and the corresponding cutoff frequencies become much lower than the MTF cutoff frequencies corresponding to an aberration-free diffraction limited system. So you see the equation 99 says that the cutoff frequencies for these MTF relationships are the same. But you know that practically we shall see that the MTF of this incoherent OTF with the aberration has cutoff frequencies which are much smaller than as the cutoff in comparison with the cutoff frequencies of the incoherent transfer function without aberration, that is k in without aberrations. Okay, OTF of an aberration-free diffraction limited system is never negative, whereas due to the presence of some types of aberrations, the resulting OTF may acquire negative values in certain regions of the spectrum. The image contents corresponding to the frequencies where the OTF takes negative values show contrast reversal. So notice very important thing, that when the OTF becomes negative at some points, then the contrast reversal corresponding to those special frequencies in the image will occur. Show contrast reversal, which means that the image contents at those frequencies may look bright at locations where they were originally dark and vice versa. So you see that contrast reversal will occur when the contrast reversal in the image will occur compared with the object where the transfer function becomes negative. OTF with defocusing. Here we are going to discuss a very simple type of error called defocusing error. We shall first write W for the defocusing problem, and then we shall find the relevant OTF. Let's assume that Zi is the distance of the image plane from the exit pupil when there is no defocusing error, and the image system produced the sharpest possible image as the system is free of aberration. Now, and let's further assume that Zd is the distance between the image plane and the exit pupil when the defocusing error is present. So we have defined two Z values, Zi and Zd, corresponding to sharply focused image and corresponding to the defocused image. In the presence of defocusing error, the new image will form either to the left side, for which Zd is less than Zi, or to the right side, that is Zd is greater than Zi of the original position of the image plane, where the new image will appear defocused or blurred. So we have discussed two possibilities, because when Zd is equal to Zi, then of course there is no there is no error, there is no defocus error. But if the defocus error is present, then the two possibilities will arise: either Zd is less than Zi or Zd is greater than Zi. The exit pupil is defined at the xy plane and the image plane is defined at the uv plane. So our exit pupil is located at the xy plane, the image plane is located at the uv plane. To keep the mathematics in the simplest form, we consider number one, an axial point source at the object plane. So zeta is equal to 0, eta is equal to 0, and the axial point image at the image plane u is equal to 0, b is equal to 0. So we have given the positions of the axial object point and the axial image point. Second, a square pupil function is considered with aperture size equal to 2w and centered on the system axis. So here we are going to consider a square pupil function with the sides equal to 2w and of course centered at the center of the coordinate axis. The third one, the spherical wave leaving the exit pupil will be considered under paraxial approximation. So again, you know that we are going to address our problems under the domain of paraxial approximations. That is, our system is isoplanatic. Figure on the next slide explains how two waves of limited dimensions, perfect spherical wave and distorted wave, emanating from the exit pupil focus at the image plane. The image point will be sharply focused point for the perfect spherical wave, whereas the distorted wave may focus either to the left of the image plane as shown in figure or to the right side of the image plane, and in both cases will form blur image or defocused image. For example, consider this example. There are two wavefronts have been shown. One is the perfect spherical wave and the other is the more curved one is the distorted spherical wave. And you know that where the two wavefronts meet, we have shown a dotted square, a dotted rectangle which indicates the pupil aperture. So this is the size of our pupil aperture, and here in this case we have shown a rectangular pupil aperture at the center of the system axis. We have shown two distances. Zi is the distance of any point xy on the perfect spherical wave from the point where it is going to be focused, and zd is the point on any xy point on the distorted spherical wave and from the point where it is going to be focused. So we have shown zd and zi, and you know that the system axis is passing through the center of the optical system, that is the center of the aperture pupil. The caption is focusing of a perfect spherical wave and a distorted wave to two different image points. So you see that we have shown our geometry, we have shown a perfect spherical wave, we have shown a distorted spherical wave, and we have also shown the two positions at which they will be focused. And you know that here in this case the distorted spherical wave will be focused to the left of the sharp focus point, because the sharp focus point is related with the perfect spherical wave. Now we consider only the paraxial part of both waves. So for the both waves we are going to discuss their paraxial waves, paraxial region, you know, that is isoplanatic region for both wave fronts. Consider a point xy on a perfect spherical converging wave incident at the pupil, and its contribution on the axial image point u is equal to 0 and v is equal to 0 can be represented by. So you see that we can represent the spherically converging wave front as a over rp. P stands for perfect spherical wave, e to the power minus iota k rp. So you know that rp is actually the distance from any general point to the point of a focus, and rp, you know, that is equal to x square plus y square plus zi square, the square root of all these quantities. And we can here we are assuming that zi is much greater than, that is zi square is much greater than in comparison with x square plus y square. So we can expand the square root as shown in the next step. We have taken zi common, and the square root contains 1 plus x square plus y square over zi square. So we can expand the square root of that quantity, and then you know that we have the binomial expansion. And at the rightmost in equation number 100 we have rp is approximately equal to zi plus x square plus y square over 2zi. So you see that under the condition that zi is much greater than in comparison with that is zi square is much greater than in comparison with x square plus y square, we have written down this expression for the rp. You know that rp in the spherical equation exists at 2 points. One is the amplitude, that is a over rp. So RP exists over here. This RP in the amplitude will simply be replaced by Zi. And there is another RP which is in the exponent as e to the power minus iota k RP. This RP will be replaced by the RP on given by equation number 100. So you see that we have expanded equation number 100 using that where Zi square is much greater than x square plus y square, or x square plus y square over Zi square is much less than 1. RP in the denominator will be replaced by Zi and in the exponential by the equation 100. So as I said earlier that this RP in the denominator in the amplitude factor exists in the denominator. So this RP will be replaced by Zi and the RP in the exponent will be replaced by the equation number 100. So this is what we have done in equation number 101. So perfect spherical wave is equal to, we have written RP from equation number 100 on the right hand side, and then you know that we have expanded, and we have also written RP in the amplitude factor by Zi. So the second step, so the last step in equation number 101 is that is the perfectly spherical wave is of the order of a over Zi into e to the power minus iota k Zi into e to the power minus iota pi over lambda Zi, and within parenthesis we have x square plus y square. Similarly, for a distorted spherical wave with the similar assumptions as we used above, we can write that the distorted spherical wave is it can be written as a over rd into e to the power minus iota k rd. And here rd, and you know that in the next step we have replaced rd by the values in equation number 100, but you know that with in equation 100, but Zi is now replaced with Zd. So we have in equation number 102 we have replaced Zi by Zt in equation number 100, and we have replaced r with its value taken from equation 100 with Zi replaced by Zt. And you know that expanding this one, and the final result in equation number 102 will be read as that is the distorted wave has the form of the order of a of approximately equal to a over Zi into e to the power minus iota k Zd into e to the power minus iota pi over lambda Zt, and within the parentheses we have x square plus y square. Ignoring the constant amplitude terms, that is e to the power iota k Zd, and in this case e to the power minus iota k Zi, these are the constant phase terms. So ignoring the constant phase terms and the constant phase terms, constant amplitude terms and the constant phase terms in the above two equations, we can write the phase factors for the perfect spherical wave and the distorted wave in the following form. So you see that this is the a over Zi. Here in equation number 102 it should be a over Zd, not Zi in equation number 102, and in equation number 101 it is correct, that is a over Zi. So you see that these a over Zi and a over Zd in equation number 102, these are the constant amplitude terms and should be disregarded, and similarly e to the power iota k Zi and e to the power minus iota k Zt, these are the two phase terms and must be omitted for simplicity, because they will not change the physics of the problem. So 101 and 102 are written in the form of 103 and 104. So these are actually the phase factors that we have written. So phi p phase factor for the perfect spherically converging wave is pi over lambda Zi. Within the parenthesis we have x square plus y square, and for the distorted wavefront we have phi d is equal to pi over lambda Zt multiplied by x square plus y square as in equation number 104. Using equation number 103 and equation number 104, the path length error W as a function of xy, or the phase error k multiplying W of xy, can be obtained from the following equation. So we are writing the phase error k multiplying by W at the coordinate x, y is equal to phi d minus phi p, and is equal to pi over lambda, and within parentheses we have 1 over lambda c minus 1 over lambda z d minus 1 over lambda z I, and outside that we have parentheses containing x square plus y square as in equation number 105. W of xy depends on the pupil coordinates in a quadratic fashion and is maximized when x comma y is located at the corner of pupil, in which case we can write that w square is equal to x max square plus y max square. We can write equation number 105 in the following way. So you see that we are introducing w square corresponding to the maximum distance of a point xy from the pupil, from the center of the pupil, w square. So w square is the maximum square of the distance relating with x max square plus x plus y max square. So introducing that one in equation number 106, we can write kmw, and you know that the equation, the left hand side has also been modified as wm, standing for the maximum, that is the max corresponding to the maximum value. So we have k wm is equal to pi over lambda, and within the parenthesis 1 over lambda 1 over z d minus 1 over z I, and you know that outside we have x max square plus y max square, and we have replaced x max square plus y max square by w square on the rightmost side of equation number 106. And you know that we have rearranged the equation number 106 in the form as given in equation number 107, because we want to use equation number 107 over here. For example, over here in equation number 105, let's introduce equation number 107. For that one, now equation number 105 can be read as given in equation number 108, that w as a function of x comma y is equal to wm within the parenthesis we have x square plus y square over w square. So you see that we have omitted the image distances. So let me read the first statement given above. In order to make w of xy to be independent of the image distances, we can use equation number 107 and rewrite equation number 105 in the following form as given in equation number 108. Okay. Before we evaluate the functional form of OTF given in equation 96, so let me show you equation number 96. This equation is 96. So you see that we have to plug in the value of our pupil functions over here. But you know that before that we want to simplify the results, and then we shall plug in the results in equation number 96 to obtain the normalized incoherent transfer function. So okay, here we are going to do the simplifications for the exponent terms contained in equation number 96. So first of all we are using this, that is w of xm. You know that each x in that equation will be replaced by wm into x square plus y square over w square, and each y will also be, and you know that the arguments of x and y together will be replaced by wm into x square plus y square over w square. So this is what we have done in that one. So the arguments have been replaced like this. So in the two exponents we have made these assumptions. These changes has been made in the two exponents. So you see that here we are going to actually introduce in the second step, you know that we are using this form, that's the equation number 108, and that's why we have the squared terms over here. And again you know that in the second exponent we have also the squared terms over here. And then of course we have the constant term wm over w square is also present. Wm over w square is also present in this exponent and also in this exponent in the second row. And you know that simplifying the second data in the second row, we can write the third row, that is e to the power iota 2k wm over w square, and within the parenthesis we have x square plus y square plus half lambda zif x whole square plus half lambda zif y whole square. And you know that here we can introduce these squared terms in the parentheses can be replaced by alpha square and beta square as in the last step of equation 109. So here we have shown that alpha is equal to half lambda z I f x and beta is equal to half lambda z I f y. Using equation number 109 and equation number 108, that is this equation and this equation in the last step of equation number 109, the OTF, that is the optical transfer function or the normalized incoherent transfer function from equation number 96 takes the following form as given in equation number 110. So this is what we have written equation number 96 by using equation number 108 and 109. We have double integral. You know that the two people functions are contained, and then of course the exponent function which we have already simplified in equation number 109 also is contained in the numerator. And of course we have the denominator which can also be directly written using equation number 108. So let's see that can we use this one in its present form, or we need to make further modifications. People functions are generally circular or rectangular in shape. Here we choose people functions to be rectangular or square, having width 2w along the x direction and 2w along the y direction. So we are choosing here as a rectangle, as a square aperture having width 2w along the x and 2w along the y directions. And you know that now these two people functions are the general form of the people functions. When we have assigned that these people functions are actually the square peoples, the square apertures, so we can replace them with rect functions. So the first people function has been replaced by two rect functions, and the second people function has also replaced by a set of two rect functions. So you know that let me read the first rect functions. This rect is equal to has an argument equal to x plus half lambda z I f x divided by 2w. And the second rect has a function, and the second rect function corresponding to the first people has a rect of y plus half lambda z I f y over 2w. And similarly we can write for the other for the arguments for the other two rect functions. You know that there is a change of sign because the people contains a negative signs in the second people function. So we can also locate that the center of the first people function, the first rect function, is at x is equal to minus half lambda z I f x, and the second rect function corresponding to the first people has a center at y is equal to minus half lambda z I f y, and each rect has a width of 2w. And similarly for the rect corresponding to the y direction similarly has a width of 2w and is located at different values of x and y. So you see that here in this step we have combined the two rect functions with the x coordinate with the fx values or x value or fx space variables, and in the second we are combining the two rect functions having y variables. And so we have the two set of rect functions contained in the curly brackets. So from the first curly bracket we can write the single rect function, that is the rect of x divided by 2w minus lambda z I over fx. And the second curly bracket, the two rect functions can be combined into a single rect function at y over 2w minus lambda z I f y. So in the last step of equation number 111, the first rect function on the left exists at x is equal to 0 with a width of from minus half of 2w minus lambda z I f x to plus half of 2w minus lambda z I f x. And the second rect function is centered at y is equal to 0 with width minus half of 2w minus lambda z I f y to plus half of 2w minus lambda z I f y. And these are explained, you know that in the figure we just show over here. The two overlapping rect, you know that when we have these rect functions, of course they have some area which is overlapping. And we show the overlapping area in this diagram. You know that in this diagram, this area we have drawn these in one dimensional form. So you know that here these are two dimensional, but we have shown only one dimensional rect functions, so we can simply explain the one dimensional figure. So look at this figure. So you see that this rect function on the left is centered at x is equal to minus half lambda zi f x, and the second rect on the right hand side is centered at x is equal to plus half lambda zi f x. So the two rect functions overlap in the region at x is equal to 0. So this rect function, which is an overlap and has been shown as in the form of gray color, is centered at x is equal to 0 and has a width of 2w minus lambda zi f x. So this overlapped area can be shown as by the first rect given in equation number 111, that is the rect of x over 2w minus lambda zi f x. And similarly, we can also draw a figure similar to this figure, but along the y direction, and on the horizontal axis we have the x parameter, y parameter. Similarly, we can justify the second rect function in equation number 111. The two overlapping rect functions along the x direction with the indication of overlapped area are shown in figure. A similar figure can be drawn for the rect along the y direction. So we have explained this rect function. The caption is two rectangular people functions and the overlapped area. And you know that we have defined this overlapped area by a single rect function as given on the left hand side of equation number 111. Now you know that we can replace these people functions, that is p people function in equation number 110 by the corresponding rect functions. So we have shown the rect functions over here in equation number 112. So the people functions have been replaced by the corresponding rect functions, and similarly in the denominator we have replaced the rect function, that is the people function has been replaced by the rect functions. You know that rect functions can be replaced by unity, but we have to replace the corresponding integral limits. For that one we are going to do this one. So in equation number 113 we have written equation number 112 in the form of equation number 113, but you know that here we have removed the rect functions in the numerator as well as in the denominator, and we have changed the limits on the first integral from minus sigma to plus sigma, on the second integral in the numerator from minus epsilon to plus epsilon, and in the denominator we have replaced the limits from minus tau to plus tau on the first integral, and similarly on the second integral from minus tau to plus tau. And you know that here there is a factor common, which is e to the power iota 2 gamma multiplying with x alpha square plus beta square. This is independent of the parameters of the integral, so has been taken out. And now you know that we have in the last step of equation number 113 two integrals which we have taken as from 0 to plus sigma and from 0 to plus epsilon. Because it is an even function, the integrand is an even function. So we have changed the limit from 0 to the upper limit, and we have multiplied this integral by 2 for each integral. So we have multiplied the numerator by 4 actually, which has been cancelled by the numerator, by the term in the denominator, because we have also modified the limits in the denominator from 0 to plus tau on the first integral and from 0 to plus tau from the second integral, and from each integral we have 2 from each integral, so multiplying 2 with 4 we have 4. So the 4 from the denominator has been cancelled with the 4 from the numerator. The 4 factor came from the adjustment of the integral limits in the second step of equation number 113. So what are these sigma and epsilon and tau? This is what we have introduced, explained over here. So symbols used are defined as sigma was set w equal to minus half lambda zi fx, and that is equal to w minus alpha because we have introduced alpha already, and that is equal to w minus w within bracket we have a minus 1 minus fx over f0i, and similarly epsilon is equal to w minus half lambda zi fy. So it is equal to w minus beta is equal to w within bracket 1 minus fy over f0i, and similarly we have defined tau is equal to w, and we have introduced gamma is equal to k into wm over w square. And you know that substituting the value of w over substituting the value of k over here, which is 2 pi over lambda, and rearranging the term in this suitable form, we have obtained that is gamma is equal to pi into 8 wm over square of 2w multiplying by 1 over lambda as in equation number 114. And you know that we have used alpha is equal to w into fx over f0i, and we have used beta is equal to w into fy over f0i. So that's why we have changed the limits according to that. And let's read integrands in equation number 113 are even functions of x and y variables, and each integral will be twice in its value with half the limits. The integrals are separable in x and y variables, and we can write equation number 15 as given on the next slide. So these two integrals are now separable, that is the integrals in the numerator and the integrals in the denominator can be separated out depending upon the x and y coordinates separately, as we have done in equation number 115. So let's compute. We have a constant term outside these integrals, so let's compute this constant term first, substituting the value of alpha square and beta square as in equation number 116, and simplifying that one we have obtained the term on the right hand side in equation number 116. And now let's simplify the integrals in the numerator. So the integral in the numerator, we are going to solve one of the integrals from 0 to plus sigma, and the integrand is e to the power iota 2 gamma x square integration with respect to dx. And you know that introducing the parameter that is 2x square is equal to t square, and t is equal to 2 under root x below the equation number 117, making these substitutions, and the modified upper limit is plus square root of 2 into sigma, and the lower limit will remain the 0, And you know that the integrand parameters are replaced in terms of the parameter t. And you know that we have simplified the integral as given in on the right hand side in equation number 117. Similarly, we can also write the other parameter, other integral. So the in y, and that integral has also been written directly as given in equation number 118. So substituting these integrals in the, so one set of integral from the numerator and from the denominator has been shown. So you see that, look at the limits of these integrals. Now we can also represent tau, or we can also represent sigma in the upper limit in terms of omega, in terms of w. So in the second step of equation number 119, we have represented the full form of sigma, which is the upper limit is now plus square root of 2 into, sorry, this is not sigma, but the upper one is sigma, but here we have w. So in the last step of equation number 119, the integral in the numerator has the upper limit as plus square root of 2 into w, within the parenthesis we have 1 minus fx over f0i. And you know that the integrand is e to the power iota gamma t square over dt. And you know that the integral in the denominator is from 0 to plus w with the same integrand. So you see that by inspection we can directly write down the solution of this integral, that is 1 over square root of 2, which is outside these integrals. And you know that the integral is written directly from comparing the upper limits of the integral in the numerator and the denominator, which is the square root of 2 into 1 minus fx over f0i. And of course, the square root of 2 will be cancelled out, and we have in equation number 119 the solution of the one set of integrals from the numerator and the denominator as in the parenthesis as 1 minus fx over f0i. And similarly, you see, we can written equation number 120. So this has a similar description as given for the equation number 119. So we have solved the integrals, and now we are substituting the values of the integrals in equation number over here, in equation number 115, and then you know that we are getting the result in equation number 121. So this was the phase term, that was outside constant term we have written, and then you know that these two, that's 1 minus fx over f0i and 1 minus fy over f0i, these are the contributions from the two set of integrals given by equation number 119 and equation by 120. So our integral has been solved, and we have obtained the final result, that is the normalized incoherent transfer function including the operations is given by this factor, which is given in equation number 121. In writing equation number 120, we have assumed that w minus alpha is greater than 0 and w minus beta is greater than 0. In order to incorporate other possibilities, we may write equation number 121 in the following form. So we have introduced, we have replaced fx by fx mod, and we have replaced f by fy mod, so that we can include the other possibilities. And then you know that in equation number 121, the parameters in the parentheses can be replaced by the triangular function as given in equation number 123. So we have triangle function of fx over f0i, and we have the triangle function of f by f0i as given in equation number 123, where this inverted triangle, where this is the triangle, the symbol is the triangle, is used as a triangle function. Now equation number 123, that is this equation, gives the OTF in the presence of defocus error. If we set the path length error Wm equal to 0 in equation this, if we set Wm is equal to 0, you will get K in with aberration is equal to K in without aberration. That is, no defect error is present. The original incoherent transfer function is obtained in the presence of defocus when you set Wm is equal to 0. If we set the path length error Wm is equal to 0, the quadratic phase factor is removed and the OTF of a diffraction limited aberration free system is obtained. And you know that here in this case the aberration is defocus error. So you see that now we want to plot this function, and we want to plot the real part of this function. So for the real part, you know that this exponential factor will be removed, and only the two triangular functions will be obtained. And now we are going to plot these two obtained functions. But you know that we are going to plot this function. You can see the plots. But here you know that Wm over lambda is the defocus factor which we are going to introduce, which we are going to set equal to A, and we are changing the value of A for these plots. So Wm over lambda will be changed for these one. And you know that when we take the real part of that one, it becomes cos of pi. So exponential will be removed. So the real part of this exponential with iota is the cos of pi 4Wm over lambda, and within the curly bracket we have the terms fx over f0i whole square plus fy over f0y whole square. So you see that since we are taking in the real part, we are including the cosine of the exponent factors. So we are going to plot this one. So on the vertical side we have the real part of the incoherent normalized incoherent transfer function, and on the right hand side we are going to plot fx over f0y. Since this is a one-dimensional plot, we are going only to plot this triangle, first triangular function, which contains fx over f0i. The other is not going to be plotted because that will involve two-dimensional plot. So just we are plotting, and you know that on the left hand side we are going to plot kn with the operation as a function of fx only, not fy, which you can see over here on the vertical axis. And look at these plots, the plot with a is equal to 0, that is no aberration, that is no defocusing error is present. You can see that the normalized incoherent transfer function starts from 1 and is going to decrease linearly because the triangular function goes linearly, and you know that it is going to approach the cutoff frequency again at fx over f0i equal to 1. But you know that if you set the defocusing error different values, for example a is equal to 0.2, you can look at the graph of a is equal to 0.2. You see that it is going to in the negative direction, and then you know that it again approaches to the 0.1, where the cutoff frequency of the system is the same, almost not the same for all the points, but you know that different. So for a is equal to 0.2, the cutoff frequency is 0.8. And for a is equal to 0, the cutoff frequency is 1. So you see that in each case the cutoff frequency is also changing. But we have plotted these functions up to the cutoff frequency of the system with no aberration, that is up to 1 value, that is fx over f0i equal to 1. Now look at a is equal to 0.4. So you see that it is going to even touching the x-axis and going in the negative direction below 0.6, and you know that then it rises and then again it approaches to the value of 1. And similarly, so look at the value a is equal to 1.2. So you see that it is going to 0 below the value of 0.4, approximately just above 0.3 on the horizontal axis. So it is going to be negative at that point, and then you know that again going to be negative, and then it increases, it rises, again it touches the axis at you see just below 0.6, and then it approaches it goes in the positive direction, then again it decreases, goes again in the negative direction at a value approximately 0.7 or maybe 0.75, then you know that it goes in the negative direction, then again it goes in the positive direction at a value of maybe 83 or something like that, and then it goes and then it reaches to the value of 1. So you see that at different values of defocus, there are fluctuations in the real part of the incoherent function. Let's read the statements corresponding relevant to this figure. To visualize the shape of OTF of an aberrated system, we consider only the real part of OTF from equation number 123, which is plotted in the figure for different magnitudes of defocus error given by Wm over lambda is equal to A, as in equation number 124. So we have used different magnitudes of defocusing error in this figure. As you can see that we have drawn for A is equal to 0, A is equal to 0.2, and up to A is equal to 1.2. And you see that the plots has shown different shapes. The straight line corresponds to the diffraction limited aberration free system with a cutoff frequency equal to f0i. For increasing value of the defocusing error, the effective cutoff frequency becomes significantly lower than the actual cutoff frequency. So you can see that the frequencies, the cutoff frequencies for greater defocusing error, you know that it becomes smaller and smaller. For increasing value of defocus error, the effective cutoff frequency becomes significantly lower than the actual cutoff frequency. The frequencies where the OTF becomes negative, the corresponding image frequencies would undergo phase reversal. That is, at those frequencies, the image contrast is reversed. So you see that the points where our transfer function goes in the negative direction, that is becomes negative, then at corresponding to these frequencies, corresponding to these spatial frequencies in the image, the contrast reversal is noticed. The lower frequencies around the zeroth order frequency are less affected by the aberration. So look at this one. You know that under point 2 on the horizontal axis, look at that there is no significant difference between the transfer function, between the incoherent transfer function. So the incoherent transfer function stays the same for spatial frequencies which have lower frequencies. So for the lower frequencies are not much affected by the inclusion of defocus error. The lower frequencies around the zeroth order frequency are less affected by the aberration. To show the contrast reversal due to aberrated OTF, two spoke images are shown. Contrast reversal is evident at higher frequencies in the spoke image on the right. So look at this image. On the left image we have an image which has this is an image with no defocus, and on the B we have an image with some defocus error, and the magnitude of the defocus error is shown, that is A is equal to 0.2. If you look at the caption, comparison of images recorded with the different OTFs. Number A, spoke image recorded with the diffraction limited OTF with zero defocus, and in B, the spoke image recorded with an aberrated OTF with the defocus error Wm over lambda is equal to A is equal to 0.2. And you see that if you very carefully look, you can also notice a defocus over here. And if let's look at the plot with 0.2. So this is 0.2, you know. The defocus error is occurred at a frequencies with magnitude greater than 0.8. Because the curve becomes negative beyond 0.8 for a value of A is equal to 0.2. So you see that here is the phase reversal could be noticed for those frequencies which are higher beyond this, because for that one the transfer function is negative. So you see that here these are the frequencies which are close to the center. You can notice the contrast reversal. That is in continuation from the previous from the signal coming from the edges. You will see that the contrast reversal has been noticed. And you know that over here in this figure we have plotted the real part of what? Real part of equation 123, and you know that real part has also been shown in equation number 125. So on the second previous slide we have plotted the one-dimensional but the real part of equation 123, which is given below as in equation number 125. So the real part of the normalized incoherent transfer function with the aberration, and the aberration in this case is the defocus error as a function of fx, fy is equal to cos of terms in the square bracket are pi into 4 Wm over lambda, and within parentheses we have fx over f0 y whole square. And you know that a single direct function triangle function has been chosen with argument fx over f0y, because we want to have only one dimensional plot in this figure. Apart from the contrast, so let me read the text relevant to this diagram. Apart from the contrast reversal in image B, closer to the highest spatial frequencies which in the center of the spoke target, the image in B has blur edges even at lower spatial frequencies which lie at the boundary. This is because the edges have high spatial frequencies and in this case lie outside the cutoff frequency region of the aberrated OTF. So what this means? This means look at the outer boundary of this spoke image in B. You know that at the outer boundary we have some blurriness, and also we can observe some contrast reversal. because the blurriness and the contrast reversal is because the higher frequencies lie in the region where the transfer function is going to be negative. So due to that negative, because the edges, the Fourier frequencies corresponding to edges is high, so that's why the frequencies corresponding to these edges also lie in the same region in which the data corresponding to the center of the spoke image lie. So that's why the edges are blur and contrast reversal even at lower frequencies, and at the higher frequencies in the center they are very prominently seen. Contrast reversal is very prominent. So the corresponding edges in A are sharp. It is because their special frequencies fall within the cutoff region of the diffraction limited OTF under very severe defocus error. So we are going to discuss a very severe defocus error when Wm is much greater than lambda. And you know that then K in, that is the incoherent transfer function with aberration, has an effective cutoff frequency very close to 0th order frequency, and beyond that cutoff frequency the OTF fluctuates much faster with diminishing magnitudes. OT can then be treated as the point spread function having one central lobe and highly fluctuating side lobes. So you see that under the condition that Wm is much greater than lambda, then you know that the cutoff frequency will be very close to 0, and the data will fluctuate very high fluctuations with the diminishing amplitudes. So you see that under such a condition the transfer function will behave as the point spread function of the system, like sinc function, because the sinc function also goes in the negative direction also. So you see that when Wm is much greater than lambda, the K in will behave like a sinc function, that is the point spread function, because the sinc function goes in the negative direction also. But you know that this K in with very high defocusing error as a function of x and y will behave as like a sinc function, that is a point spread function, that will behave like a point spread function having one central lobe and many fluctuating side lobes with the diminishing amplitudes. The OTF may then be named as a synthetic point spread function. The actual PSF of the incoherent imaging system under very severe defocus would then be the Fourier transform of the synthetic point spread function, which would resemble to that of a square light spot at the image plane. This may be approximately written in the following form. So you see then under very high defocusing error, our transfer function will behave as a synthetic point spread function, and the actual point spread function under this condition is the Fourier transform of this synthetic point spread function, and the synthetic point spread function will be equal to the sinc function or the rect function. For example, a real point spread function is equal to the Fourier transform of the transfer function, incoherent transfer function under highly defocusing error, that is Wm is much greater than lambda, is equal to the Fourier transform of the synthetic point spread function is of the order of a rect function, because you know that rect has in point spread function, a rect has a point spread function which resembles sinc function. So that's why the real point spread function will behave like a rect function, because the transfer function will behave like a sinc function, and the Fourier transform of the sinc function is a rect function as given in equation number 126. So our transfer function will behave as a sinc function, and the Fourier transform of that sinc function will give you a rect function. So real PSF will be a rect function as given in equation number 126. Figure presents the schematic of an incoherent imaging system with a severe defocus error, in which case the image of a point object would appear to be a square shaped spot which can be defined by a rect function. So in this figure, our object is a point source and our image is a rectangle. Because is a square or a rectangle, whatever the case may be, is a rect function, because this is the point separate function, and you know that the image of a point separate, the image of a point source is actually called a point separate function. And you know that in this case, our point separate function, the real point separate function in the case of a very high defocusing is a rect function. So you see that this is a demonstration of a rect. The image of a point object is the shape of a rect function. We have also shown the z0, the object distance, and zi, the image distance. And the caption is image of a point object under a severe defocused incoherent imaging system. And you know that I have shown the exact pupil of the system also. The exact pupil of a severe defocusing error has also been shown, which is of the shape of the rect function, which is a rectangular in shape. Okay. We have assumed the exit pupil in the form of square aperture. Point separate function defined by a rect-like function can be justified with the geometric optics treatment of light, which is also shown in the figure. We can disregard the contribution of diffraction light in this case. That is, in the case of a very high defocusing error, we can disregard the aberration, we can disregard the diffraction, and the image that will be formed can be explained simply with the geometric optics. This is the end of slide number 61.